4-port network. A 4-port network S matrix contains 16 elements. The S matrix has the following form. It is a 4x4 matrix. Further, if all ports are matched, then S11, S22, S33, and S44 are all 0. Further, if the device is a reciprocal device, S12 is equal to S21 and S13 is equal to S31 and so on. One example of a 4-port network is the directional coupler. There are two different type of directional coupler which has a different S matrix. One looks like this and another one looks like this. The first one, S12 is alpha and S13 is J beta. What it means is that the output at port 2 and port 3, when signals is fed to port 1, the magnitude at the output of port 2 is alpha and the magnitude of the output at port 3 is beta. The J means there is a phase difference of 90 degrees. Another type of directional coupler, the output at port 2 and port 3 are alpha and beta respectively, but they have the same phase. This is the case if we feed the signal to port 1. If we look at S24 and S34, we see that the output is alpha and negative beta instead. What it means is that if we feed the signal to port 4, the output at port 2 and port 3 will have a phase difference of 180 degrees. The important parameters of directional coupler include coupling, directivity, and isolation. The directional coupler is generally a 4-port network. If we input the signal to port 1, most of the signal will be transmitted to port 2. So port 2 is called the true port. A fraction of the input power is coupled to port 3. So port 3 is called the coupled output. Whereas for port 4, ideally no signal should be coupled from port 1 to port 4. That means port 4 is isolated from port 1. Therefore, it is called the isolated port. This is for the case when the signal is fed to port 1. If we feed the signal to port 2, this time the signal will be transmitted to port 1. A fraction of it will be coupled from port 2 to port 4. So in other words, in the reverse path, port 4 becomes the coupled output, whereas port 1 becomes the true port. And this time port 3 becomes the isolated port, which is isolated from port 2. The amount of power that is coupled from port 1 to port 3 compared to the input power P1, this ratio is called the coupling or coupling factor. Taking 10 log of the power ratio will give us the value in dB. If we input a signal to port 1, ideally no signal should be coupled to port 4. But practically, a small leakage may occur. So if we take the ratio of the power input to port 1 compared to the undesirable leakage to port 4, this ratio is called isolation. The difference between the value of isolation and the coupling factor is called directivity. In other words, directivity is the power coupled from port 1 to port 3 compared to the power coupled from port 1 to port 4. Therefore, we have this formula, 10 log of P3 over P4. Notice that we can't measure directivity directly, typically. We need to measure coupling factor, that is the power coupled from port 1 to port 3. And then next we need to measure the isolation by measuring the power coupled to port 4. And we can then calculate directivity by taking the difference between I and C. Some typical directional couplers include hybrid coupler, which are directional coupler with a coupling factor of 3 dB. In other words, half of the input power will be coupled to port 2 and half of the power will be coupled to port 3 when the signal is fed to port 1. In terms of the S matrix, we will have alpha equals to beta, which is equals to 1 over square root 2. Because alpha and beta are the voltage ratio instead of the power ratio. There are two types of hybrid couplers. One hybrid coupler is called the quadrature hybrid. Another one is called the magic T or red phase hybrid. In the case of quadrature hybrid, the output at port 2 and port 3 has the same power, but the phase difference is 90 degrees. In the case of 180 degree hybrid coupler, such as magic T or red phase hybrid, the output at port 2 and port 3 are the same if the signal is fed to port 1. They have the same magnitude and phase. But if the signal is fed to port 4, the power output at port 2 and port 3 will be equal in terms of the magnitude, but they have a phase difference of 180 degrees. The branch line coupler is an example of quadrature hybrid. That means 3 dB directional coupler with 90-degree phase difference in the output. This is the construction of a branch line coupler. It consists of 4 quarter wave lines. Between port 1 and port 2, we have a quarter wave transformer with a characteristic impedance of ZC over root 2. The same goes for the quarter wave transformer between port 3 and port 4. The other two transmission line or quarter wave transformer has a characteristic impedance of ZC. The S matrix looks like this. The two output at port 2 and port 3 has the same magnitude but phase difference of 90 degrees. That means when the signal is fed to port 1, this signal will be transmitted to port 2, and at this T junction, half of the power will be directed to port 3. Therefore, the power output at port 2 and port 3 will be equal, but the phase difference is 90 degrees because of the quarter wave line, which gives rise to a phase shift of 90 degrees. No signal is coupled to port 4 because from port 1 to port 4 we have a quarter wave line which gives us a 90-degree phase shift, and from port 1 to port 2 and then to port 3 and then to port 4 there are 3 quarter wave lines which give rise to a total phase shift of 270 degrees. That means the signal that goes from port 1 to port 4 through 1 quarter wave line and the signal that is transmitted through 3 quarter wave line to port 4, these two signals will have a phase difference of 180 degrees. And because of the opposite phase and the similar amplitude, the two signals will cancel each other ideally. Therefore, the output at port 4 will be 0. Of course, this ideal performance only occur at one frequency, that is when the transmission line length is exactly 1 quarter wave length. At other frequency, the performance will be degraded. Another type of hybrid coupler is the 180-degree hybrid coupler. If we apply a signal to port 1, the output at port 2 and port 3 will have the same magnitude but and also the same phase. But if the signal is fed to port 4, we will also have the signal output at port 2 equals to the power at port 3, but this time the two outputs will have a phase difference of 180 degrees. So this kind of 180-degree hybrid is very useful to combine two signals. If we apply two different signals to port 2 and port 3, the output at port 1 will be the sum of the two signals, and the output at port 4 will be the difference between the signal at port 2 and the signal at port 3. So that means we can get the sum of the two signals and also the difference between two signals connected to port 2 and port 3. This is one example of the magic T or rat race circuits. The S matrix looks like this. If we input a signal to port 1, the T junction will split half of the power to port 2 and the other half to port 3. But none of the signal will go to port 4 because from port 3 to port 4 we have 1/4 wave line, whereas from port 2 to port 4 we have 3/4 wave line. That means the signal that is transmitted from port 3 to port 4 compared to the signal that is transmitted from port 2 to port 4 will have a phase difference of 180 degrees, and therefore they will cancel each other at port 4. That means no signal will be transmitted to the output port of port 4. Half a signal that goes to port 2 and half of the power that goes to port 3 will have the same phase because the amount of delay is the same. But if we input the signal to port 4, half of the signal will go to port 3 due to the T junction, half of the power will go to port 2. Because the distance from port 4 to port 3 is 1/4 wave long, and the path length from port 4 to port 2 is 3/4 wave length. So therefore the phase difference between the output at port 3 and the output at port 2 will have a phase difference of 180 degrees. This time no signal will go to port 1 because any leakage from port 3 to port 1 and leakage from port 2 to port 1 will have the opposite phase as we mentioned just now, and they will cancel each other. What we have seen earlier are the hybrid coupler where the coupling factor is 3 dB or half power at the two output ports. In some applications, we only want a small fraction of the input signal to be coupled to the coupled port. One simple solution is to use a pair of parallel transmission lines with a small spacing between them. The stray capacitance and stray inductance of the transmission line give rise to crosstalk. That is why a fraction of the signal can be coupled from one line to another. But we wish to control exactly the number of dB that is coupled from one line to another. So we need to analyze how the signal is coupled from one line to another, and because the parallel transmission line is symmetrical, we can use the even and odd mode analysis that we studied earlier. Consider two signals V1 and V2 connected to the pair of transmission line. Voltage V1 and V2 can be considered as the sum of a pair of even mode signal and a pair of odd mode signal, where V1 is the even mode voltage plus the odd mode voltage, and V2 is the even mode voltage minus the odd mode voltage. Therefore, we can analyze the output due to even mode excitation and the output due to odd mode excitation separately. The final output will be the sum of the output from even and odd mode excitation. The transmission line individually has a certain characteristic impedance ZC. When the pair of transmission line is fed with odd mode signal, due to the coupling between the two lines, there will be a different characteristic impedance, or in other words, the characteristic impedance is affected. We will get a different value, which is ZOO, stands for the characteristic impedance under odd mode excitation. Similarly, under even mode excitation, the effective characteristic impedance will be ZOE, or even mode characteristic impedance. Based on ZC, ZOO, and ZOE, we can find a formula to calculate the coupling factor. This is what happened under even and odd mode excitation. Under even mode excitation, because the two parallel lines has the same voltage, there is no coupling from one line to another. So under this condition, we have even mode characteristic impedance given by this formula, where V is the propagation velocity and CE is the capacitance between the strip and the ground plane. Under odd mode excitation, the voltage are of the same magnitude but opposite phase. That means when one line has a positive polarity, the other line has negative polarity. Therefore, there are electric field coupling from one line to another. So the capacitance that the signal will experience will be different. That capacitance is CO, or the capacitance under odd mode excitation. It can be shown that the voltage coupling factor, or the voltage at port 3 divided by the incident, the input voltage. This is the port where we input the signal. A fraction of the signal is coupled to port 3. the voltage at port 3 divided by the voltage at port 1 is the square root of the power at port 3 divided by the power at port 1. ZOE is given by this formula and ZOO is given by this formula. So based on the desired coupling factor C, we can calculate the required ZOE and ZOO, and then we can use this graph to find the required line width and spacing. For example, for a given value of ZOO and ZOE, we have a coordinate on this graph. If we follow the line to this side, we will get W over D. And then for the same point, if we follow the line to this field, we will get S over D, where S is the spacing between the two lines and D is the thickness of the board. This is how a couple line directional coupler looks like. It basically consists of a pair of microstrip lines separated by a small gap. The 4 ports are connected to separate connectors, and it can be put inside a box with 4 connectors that look like this. Typically, one of the output port is terminated by a match load. That is the isolation port. A better coupler is the Lange coupler. This is how it looks like. A Lange coupler can be made to have a coupling factor of 3 dB or less. If we input a signal to port 1, we will have a signal coupled to port 3, and then a fraction of it is coupled to port 2. This fraction can be half power or less. Due to the spacing of lambda over 4, the two outputs will have a phase difference of 90 degrees. In the design of Lange coupler, we will need additional bonding wire from here to here, from here to here, from here to here, and here to here. It is basically consists of a number of parallel lines. So this construction gives us a much wider bandwidth. This is a modification of the Lange coupler to reduce the number of bonding wires.